Hello, my name is Dr. Holly East and I am a Senior Lecturer in Physical Geography at Northumbria University, which is in Newcastle in the northeast of England. My research is primarily focused on the Maldives, on both coral reef island development and evolution, and also seagrass meadows. Thank you very much for inviting me here to speak today. I'm only sorry that I'm not presenting live, but thank you very much for letting me be a part of the symposium. So today I'm going to talk about seagrass meadows and their role as a potential source of reef island building sediments. So coral reef islands are low-lying, typically less than 3 meters above mean sea level, accumulations of sediment that are deposited by waves on coral reef platforms. They're of key ecological importance as they provide habitats for threatened and endemic species, and they're also of socio-economic importance as they provide the only habitable land within atoll nations, including the Maldives. However, coral reef islands are perceived as being among the most vulnerable environments to climate change and especially to sea level rise. And that is because they are very low lying, so as we said, typically less than 3 meters above mean sea level. They're formed of largely unconsolidated sediments and they're reliant upon a locally generated sediment supply both to build and maintain their shorelines. So this reliance on a locally generated sediment supply is given that reef islands are formed entirely of sediments produced by the organisms living in their surrounding marine environments. That sediment is then transported by waves and it's to nodal points of accumulation and they build up over time to form an island. However, our understanding of these linkages between the reef ecology and the island building, island geomorphology, is very limited. We do have some emergent understanding of some sediment producers and their role in contributing to reef island building, so for example parrotfish. However, there's a lack of knowledge about sediment production associated with some other organisms and other sediment producers. We do know that islands in the Maldives are formed predominantly of sand-sized material, and that is because anything smaller, so the muds and silt-sized material, is typically washed off platforms by waves and into deeper waters. It's lost from the reef platform system itself. And one of the sediment producers that we have a real lack of knowledge of is seagrass. So the hypothesis we wanted to test in this work was that seagrass meadows potentially are contributing to reef island building through sediment production. So how would that sediment production happen? It is associated with the epibionts, so made of calcium carbonate. So if we look at the blades of seagrass, we see that there's this white stuff on the seagrass leaves, on the surface of the blades. Zooming in on this, so these are some pictures taken through the microscope of seagrass leaves. We can see we've got these calcareous creatures, epibionts, crusters, coralline algae, foraminifera, bryozoans, gastropods that are living on the seagrass leaf surface. So when these calcareous epibionts die, or when they break off the blades, or when the blades die, then that calcium carbonate is contributing directly to the sediment reservoir, and it may then go on to contribute to coral reef island building. Why is this important? It's important in part because seagrass is removed actively and routinely by many resort islands in the Maldives. Since I started this work, a campaign has started to protect seagrass in the Maldives, Blue Marine Foundation, which is fantastic. And so we're hoping with our research that we could add an extra argument to that case for seagrass conservation. So our research questions were to try to determine what are the rates and types of sediment production associated with seagrass, and what proportion of that material is of an appropriate grade, so sand-sized material, to contribute to coral reef island building. Our study site was on Huvadu Atoll, which is the second most southerly atoll in the Maldives, and we were working towards the south of the atoll, on a seagrass meadow off the oceanward coast of the island of Vati Huta. For our methodology, we began by identifying a series of seagrass zones on the basis of seagrass leaf densities, percentage covers, and species composition. We identified these zones on the basis of field data and drone UAV imagery. We then mapped the zones using satellite imagery at a spatial resolution of 3 meters and performed a maximum likelihood classification to produce a map of those zones. We then used these zones to structure our sampling design for the remainder of the study. So we first undertook in the field seagrass blade density measurements or leaf densities. So that's where there were 2 species in our site, Thalassodendros pileatum and Thalassia hebrichii, and we counted the blades manually of each of these species in 25 centimetres square quadrats. In total, that we did 300 quadrats, within which we counted over 27,000 blades of seagrass individually to give us the most accurate characterisation of the leaf densities that we could. We then also collected a series of 400 seagrass blades, that's with an equal number of blades of each species and within each zone. And we analysed these in the lab, which you can see Grace doing here, using the weight loss after acidification method. And this is to determine the total mass of sediment that was associated with each individual blade of seagrass. To determine how much of the material is the right type to contribute to island building, we're looking at the grain size, for which we collected a series of bulk samples of seagrass, so 24, an equal number of each species in each zone. And we carefully hand scraped the blades of each of those bulk samples to remove the epibionts. We then looked at the grain size of those epibionts in the masticizer. However, we then analysed these samples again after a period of 21 days continuous agitation. And that was to simulate the wave action upon the sediment over a period of 21 days, because ordinarily that material would need to be transported by waves from the seagrass meadow to the island itself. So here we have our study site here on the left, so the seagrass meadow off Vati Huta Island, and here we've got the classification that we produced using the satellite imagery at a spatial resolution of 3 meters and with a classification accuracy of 98%. You see we identified 3 main zones, one of which was divided into 2 sub-zones. So what were the characteristics of these zones? So starting towards the oceanward side of the platform, we had zone 1 here, which was dominated by rotundata. We had zone 3 dominated by hebrichii, and in between a more of a mixed species zone, which was characterised by more continuous seagrass coverage in contrast to the more circular patch type growth found in zone 3. So how much of the sediment was of the right type to contribute to reef island building? So here we've got the grain size graphs for our sediments collected from the seagrass, the epibionts. All of the material to the right-hand side of this dotted grey line is sand-sized material. And we found that in all cases, sand-sized material accounted for the majority of sediment associated with seagrass epibionts. And that included after 21 days of continuous agitation, simulating wave action at about 61% of sand-sized material of the right type to build an island. So what are the rates of sediment production? So we can see here we've got per blade, so per individual leaf, about 0.04 to 0.08 grams of sediment. We then quantified the rates of sediment produced. So this is in kilograms per metre squared per year. We found variation up to about 1 kilogram sediment production associated with seagrass meadows. And of that material, as we said, the majority was sand-sized, up to about 800 grams, 0.8 kilograms of sediment per metre squared per year. and that is from the post-agitation grain size data. So multiplying these rates per metre squared by the total area of each zone is calculated from our satellite derived maps. We're able to estimate the total sediment production associated with Seagrass Meadows, and that was 853,000 kilograms of calcium carbonate per year. Of that material, about 541,000 kilograms per year was of the right types of sand size to build a coral reef island. And that is over an area of 1.1 kilometre squared. So to put that in context, some kind of context, that volume of material, of sand size material, would be sufficient to build the island of Vartikuta over a 16-year period. So it's a lot of extra geomorphically important material that's being added into these reef systems by the seagrass. So in summary then, here we have presented a first order estimate of the rates of sediment production associated with seagrass meadows in a coral reef island setting. We highlight from our data that seagrass is indeed a hotspot for the production of reef island building sediments. This is particularly important given that coral health, primary builder of islands in the Maldives, is declining in the region. So this capacity of seagrasses to contribute to shoreline building and maintenance, we suggest, is a highly valuable seagrass ecosystem service that has not really been recognised to date. Seagrasses are well recognised for their role as stores of blue carbon, in terms of their being valuable for biodiversity, but this is another extra ecosystem service. And so here we present, in this way, a geomorphic argument for seagrass conservation. And through this work, we'd like to emphasise the importance of recognising geomorphology as well as ecology in conservation efforts. So thank you very much for listening. If you've got any questions, if you have any comments on our work, I'd love to hear from you. My email and Twitter handle are on the screen there. So thank you very much.